I want to do one more example of solving a system of linear equations with Gaussian elimination on matrices, and particularly this is going to be a more complicated example where the answer ends up being infinite and we have to use parameters to describe the solution set. Usually you don't know that ahead of time, but I'm telling you that so that you know what to expect, so you can think about how to write these parameters in the future. So here's our linear system of equations, and we want to find the solution set. So the first thing we're going to do is we're going to try to put this linear system in reduced row echelon form. So if I'm putting this in reduced row echelon form, I want a leading 1 in the first row. That coefficient on x is 1, so I've already got it, so that's good. And then after I know I've got a leading 1 in the first row, I want all entries beneath that x, all rows beneath that to have no x term in them. So what do I need to do? I need to replace row 3 with row 3 minus 3 row 1. So if I do that, the only thing that's going to change is row 3. So row 1 and row 2 stay the same, and I take row 3 and I subtract 3 row 1. And I get, well, my x term is gone. In fact, the w term is gone too, and we get 4y plus 6z equals 10. Okay, so how do I decide what my next step is? Well, each time I say, do I have a leading 1? Are all the terms in the row but below it gone? So I have a leading 1 for my x variable in the first row. All the x variables in the equations below it are gone. So then I move on to the next row, the next equation. So I look at this equation, I want a leading 1. So I want a leading 1 on that y term. And so what I do is I replace row 2 with 1/2 row 2. And replacing row 2 with 1/2 row 2, rows 1 and rows 3 stay the same. And I replace row 2 with 1/2 row 2. After I've ensured that row 2 has a leading 1, I make sure that all equations below row 2 do not have a y variable in it. So that means I'm going to replace row 3 with, let's just keep looking at this. I'm going to replace row 3 with row 3 minus 4 row 2. Okay, so I'm going to replace row 3 with row 3 minus 4 row 2. So I'm going to do that. Rows 1 and rows 2 stay the same. And actually, row 3 totally cancels out. I get 0 equals 0, which is good that we didn't get like 0 equals 5, which would be impossible. So 0 equals 0 isn't a bad statement. But what we'll notice now is that we have a linear system in in row echelon form, where I have a leading 1 in each equation, and the leading ones go from top left to bottom right. The leading 1 in row 2 is to the right of the leading 1 in row 1. So that's good. And the reason that we want that is that it makes it much easier for back substitution. So what you'll notice is that all the variables depend on each other, but if we let z and w be whatever we want them to be, then x and y are determined. Okay, so z and w can be whatever we want them to be. They are called free variables. They are free to be whatever we want them to be, and x and y depend on them. So because of this, we're going to use parameters. We're going to let z and w be our parameters. So what we want to do is write x and y in terms of just z and w. And you'll see in this top equation, we actually have x written in terms of y, z, and w. And we want to get rid of that y. We can use row equivalent operations to do this, though. So, for example, we can take row 1 and replace row 1 with row 1 minus row 2. That will get rid of the y variable in row 1. We will leave row 2 alone. So, leaving row 2 alone, we get y plus 1.5z equals 2.5, and then x minus 0.5z plus w equals negative 2.5. So this sets us up for our solution set. We let z and w be free parameters. Those are our parameters. And then that tells us that x equals 0.5t minus s minus 2.5, and y equals negative 1.5t plus 2.5. So we have all of our variables in terms of our parameters. All right, so next up, we're going to take this same linear system and try to associate a matrix and do Gaussian elimination on the matrix. So that's what's coming in the next set of videos.